Dear students, good morning. Today we are going to discuss about this VLSI. What is the importance of VLSI and what is VLSI? VLSI is a very large scale integration. Today the technology is changing from day by day. We know all of this. So according to VLSI designers, so every 1 year there is a change in the memory, and every 1.5 year there will be a change in the size. So this is the how it is possible to increase the memory and to reduce the size. It is possible because of this VLSI technology. Day by day it is increasing. As we know today, the India is going to start chip manufacturing industries. So we need to know what is the importance of this, and we need to improve the skills in VLSI. In this, one of the important topic is FPGA design. So why FPGA? What is FPGA? Field Programmable Gate Array. So why this field programmable gate array is? So before going to design a chip, we need to verify whether our design is correct or not. How do we know this? Whether the chip, before manufacturing the chip, we need to test all the IC operations in this FPGA design. So therefore, what are the methods are going to be used in this FPGA? All this we are going to discuss in this class, and we need to check this. So first one, what is the design flow of FPGA? So you will see this. This is a basic block diagram of a FPGA design flow. So we have a design verifications, and these are the functional verifications. So in design verification, we have a basic three parts are there. One is a behavioral simulation, second one is a functional simulation, third one is the static timing analysis. So these are both are interconnected. Design verification and data process both are interconnected. So we have a behavioral simulation is connected to design entry, from design entry to synthesis. So from synthesis to implementation, and implementation to device programming. So therefore both all are interconnected. So for example, take the implementation. This implementation is connected to functional simulation and as well as statistical analysis. So now we are going to study detailedly about this. What is the basic architecture of this FPGA? So we are going to study about this synthesis and as well as implementation. Now synthesis is a process of translating the VHDL or a Verilog code. So in a design, we are going to write a code that is called as VHDL code. So we need to write a code in the form of VHDL or Verilog. So what is the VHDL or Verilog? It is a logical elements. With a logical elements, the circuit is going to be designed, and by writing a program, we are going to see the logical elements. What are the logical elements are going to be used in FPGA is, we are going to use the gates and flip-flops. So these are the basic elements are used in a FPGA technology. So in a synthesis process, basically we are writing the program. The program is going to be translated into in the form of gates and flip-flops, and it prepares the net list for the entire design. So this is the process. So for writing the VHDL or Verilog code, we are going to use this Xilinx technology. We are going to use the Xilinx, and so from this we are going to save all the data into NGC. What is the meaning of NGC is, it is a negative generic circuit. It is a negative generic circuit. This negative generic circuit consists of, so what is NGC? NGC is a negative generic, sorry, native generic. Okay. So NGC is a native generic circuit. So what is there in native generic circuit? It contains the gates and flip-flops. So these are all entire the process is done in the synthesis. So what is the next part is a implementation. So what is going to be happened implementation? The written code is going to be take part in is a translate, and second one is map, and the third one is place and route. So these three parts will be used to implement the circuit. So what is the translate? So translate is simply whatever the NGC file, that file is going to be translated to a in the form of netlist. So that netlist is going to be form the circuit. So the netlist is going to form the circuit. So the second point is the mapping. What is meant by mapping? Whatever the circuit we are designed, the designed circuit is going to be interconnected. That interconnection and all things will be done by using the mapping technology. By using mapping. So here if you see this, all the circuit with a logical elements into a subblocks. So in the mapping process, the designed and the native generated netlist will be converted into a subblocks. So in this subblocks we are going to have a different parts are there, that is called as FPGA elements. The FPGA elements are combinational logic blocks. So in a combinational logic blocks we are going to have a input output blocks and generates an NCD file. So what is the NCD file? As already we are, if you see this, NCD is a native circuit description. So that native circuit description is a physical representations, and it is a map to a FPGA. It is mapped to a FPGA. So next third one is the place and route. So the place and route is a process. It places the subblocks from the mapping process into a logical blocks. So for example, if you take placed in a logic block which is a very nearer to the input and output pin. So whatever nearer to the input output pin, that is connected to this input outputs, and the rest of them are connected internally. And between all these constraints, you take a account by place and route process. So this is three methods are used in the implementation. So next one is the design programming. What is the design programming? So whatever we are going to design an IC, that IC is going to be placed into a FPGA. We are going to place it into a FPGA. So simply we are going to convert VHDL or FPGA program into a FPGAs to test whether it is working, its functions and everything is working effectively or not. So this is the simple understanding of this. So next we are going to see this design verification. So what is meant by design verification? So whatever the circuit we are designing, is it functioning effectively or not? So how do we test this? We have a different methods are there. By using those methods, we are going to test the program, whether it is whatever the design we did working properly or not. It is done by using a design verification. So in this design verification, one of the method is RTL simulation. So in a behavioral simulation, we are going to call it as a RTL simulation also, resistor transistor logic simulation. So it has different steps to verify this design. So one of the in the process we are going to check the design flow of the program. Is it follows the conditions or rules and regulations of the program. So it is going to be verified, and whether the data is going to be flow according to design flow or not. And the second one is, so synthesis process to verify the RTL. So RTL is going to be have, as we know, resistor transistor logic. So that confirms the design is a functioning. So RTL confirms the design is a functioning or not. So it is going to be performed. We are going to write the behavioral simulation or RTL simulation by using a VHDL or Verilog designs. So one more one more important point is we are going to verify the signals and as well as the variables. We are going to verify signals are and as well as variables in this functions. So one more is it allows the designer to change the VHDL code. If a written code is not accurate or not matching with the design, so designer has to change with the HDL code. So like this we are going to verify. This is called as a behavioral simulation, and another we are going to call it as it is a gate level or timing and resources. It is going to be verify the timing and resources in this design verification. So functional simulation we are going to call it as a post translate simulation. Post translate simulation. So after the design, whatever the design is going to be verified, it is called as a post translation or functional design. Functional verification, what we are going to do? We are going to write a program and we are going to dump into FPGA. After that, we are going to verify the whether its a functionality is a good or not. So based on the functionality, we are going to finalize whether our design is a good or bad design. So in this we are going to see this, what is going to be happen in a functional simulation. We are going to see the logical operations of the circuit. So logically whether it is a good or not. So for example, if we design an AND gate, so what is the AND gate functionality? We know the truth table. If you take A and B are the inputs and Y is an output, what is the function of AND gate is Y is equal to A and B. So if you take this Y is equal to A and B, so we are going to give the inputs. If it is a 0 0 and Y is a 0, if it is a 0 1 and Y is also a 0 because of its multiplication, and inputs 1 and 0 again, inputs 1 and 0 again we know it is a 0, and similarly if we know the inputs 1 and 1, we know the output is a logic 1 because of its multiplication. So based on Y is equal to 1, then we can say this AND gate is working very effective, it gives the good circuit of the logic operation is going to be verified like this. So that is called as a post translation. So next one is it's not a expected one. A designer had to make to change if any problem is occurred and expected outputs are not getting, then the designer has to change his design, or he may write the VHDL code again. So next one is the static timing analysis. So after designing this functionality, after completion of the functional simulation, we are going to verify the static timing analysis. So what is meant by static timing analysis? So it is a post mapping time reports the list, and we need to check the signal path delays. We need to check the delays. So these delays will occur due to the implementation of the circuit. So if more delay occurs, what happens? It consumes some more time, and design is going to be failed. So we need to reduce the time. If you want to reduce the time, we need to ultimately reduce the delay. So this static timing analysis also a very important analysis. We are going to summarize these designs like this, and we have to verify the basic structure of the FPGA. So now we are going to say this. A first design is a FPGA architecture contains like this. So the structure of FPGA contains, these are the blocks, and so we have a IO blocks are there in this. We have a IO blocks. So IO blocks are called as input output blocks. So input output blocks are nothing but output pins. So for every IC we have a pins. So that pins, some of the pins are acting as a inputs, and some of the pins are acting as a output. So therefore that's why the outer edge values or outer edge blocks are going to call it as a input output blocks. So internally we have a these designs are there. This is called it as a logical blocks. So in this logical blocks we are going to have a what we have discussed previously. So basic gates and flip-flops are going to be used to design this logic blocks. So we have some interconnects are there, some wires are there. These are called as a interconnects. These are called it as interconnects. So what are the interconnects? There should be a communication between the logical blocks. There should be communication between logical blocks. To interconnect this logical blocks, we are going to use this wires. We are going to use this wires. So this is a simple and basic architecture of the FPGA. So in FPGA, we are going to see some of the important points in this. The important points are the name capability of gate arrays, and we are going to have a standard gate arrays. Standard gate arrays are going to be used. What is the purpose of standard gate areas is field programmable gate arrays or the larger devices. So it's basically it is a cell structure. So this design is a cell structure design, and so you are going to have a configurable logic blocks. So we are going to have configurable logic blocks. So in this we have three types of configurable logic elements are there. So as we are discussed already, IOBs are called it as input output blocks, and another one is CLBs. So CLB is a configurable logic blocks. Configurable logic blocks. And as we are already discussed, third one is called as interconnections. Third one is called as interconnections. These are the three are very important in a FPGA technology. So what is the function of this? So IOB provides the interaction between the internal array of the logic blocks. IOBs are going to be perform internal array of the logic blocks, and CLBs are performing the logic functions. Understand this? CLBs are performing the logic functions. What are the logic functions? We know flip-flops and gates and memories all are under the logic functions. So, and these are also going to be interconnected. So, these are also going to be interconnected. So, if you see this, programmable logic blocks are smaller and lesser capable. Smaller and lesser capable, and its memory is very less. So, that is one of the limitations of this FPGAs, and we have a other FPGAs are having more storage capacities. So, then how to design this FPGA? What are the technology is going to be used in this FPGA? So, one of the design technology is gate array design. One of the technology is gate array design. So, it is a fast prototyping capability is there, that is one of the important, and gate array implementation requires two-step manufacturing process. So, this is one of the technology we are going to use for designing this FPGAs. So, in this we are going to have a full custom mask set we are going to use, and it is also we are going to use the poly cells. So, these poly cells are different layers are going to be used, and in this it includes the few hundreds of cells. It includes the few hundreds of cells, and this we are going to have a inverters and NAND gates, and similarly NOR gates, and we are going to have a complex AOIs, and we are going to have a D-latches and flip-flops. So, all are going to be interconnected in this gate array design. And we are going to have a different fan outs also available. So, fan out is nothing but how many outputs it is going to be handled, how many outputs it is going to be handled is a fan out. So, it is a double sized and quadruple sized, and these are the different sizes are going to be used to design the circuit. So, here we are going to see the several different characterizations, and in this we are going to have so delay time versus load capacitance, and circuit simulation models, and timing simulation models, fault simulation models, cell data and place and route mask data. So, these are all going to be verified in the design. So, these are the different methods, whether timing delay is more or less we are going to verify, and it is going to be depend on the load capacitance. How much load, if you increase the load, time delay is going to be increases. If you try to reduce the load, and time delay will be reduced. So, next is a circuit simulation model. We are going to verify whether the circuit is functioning effectively or not, and similarly timing simulation model. So, we are going to verify how much time it takes for execution of the or to finish the task. So, fault simulation model, if we are going to test the nodes, so if node values it gives the according to our design, so it is going to be a good model, or otherwise we are going to identify that there is a fault in the design. And cell data and place and route, so we are going to place the all the designed values in the FPGA. So, another method is ultra flex 800 FPGA. This is the second generation of FPGA. So, in this second generation of FPGA, what is the difference between previous one and this one? So previously we are going to have input output blocks are there. So CLBs we have. So here we are going to have a external facilities are going to be incorporated in 800 FPGA. Okay, second generation of FPGA is UltraFlex 8000. So in this UltraFlex 8000, the previous one is a 4000 and it is a 8000. So there is a difference in the design. What are the basic differences we are going to observe? So we have in 4000 we have a input output blocks, as we know. Here also we have a input output blocks, and similarly we have a logic blocks also we are observed. So here logic blocks are there, but what is the additional one is we are going to have a logic array blocks. So in this 8000 FPGAs, additionally we are going to have a logic arrays. So we have a one more important one is fast track interconnects. We have a fast track interconnects is also a one of the important in the design of 8000 FPGA. So we are going to detailedly we will see this. What are the advantage of this one? In 8000 FPGA, the basic advantages are represented here. We are going to see that. So what is that? We have a 26 to 162 logic array blocks are there. Due to this, the capacity of storage is going to be increased because of this LABs. So how many LABs are there? We have a 26 to 162 LAs are there, and one more each LBA. So each LBA contains the 8 logic elements, 8 logic elements. So for example, if you multiply this 26 into 8, so how many we have? A 208 or LEs are there. So similarly 168 into 8, we are going to have 1296. So these are the LEs. So and how many logic gates we are going to use? So for this 208 LEs, we are going to use the 2500 gates, and if it is a 1296 LEs, so we are going to use how many gates? We are going to use the 16,000 gates are going to be used. This is one of the basic advantage of using the 8000 FPGAs. So it is a one more advantage, as already we have discussed. It is a fast track interconnect. Fast track interconnect. So then we will see what are the applications of this 8000. So one of the application is resistor intends to digital signal processing. In digital signal processing we are going to use. So in the digital signal processing we are going to convert the analog signals into digital signals, and we are going to use both analog signal and as well as the digital signal in this digital signal processing. And one more advantage is, so we have a wide data path. So wide data path manipulation is also a one of the important application, and the third application is data transformation. Data transformation, converting data into one form to another form. So this 8000 FPGA plays a vital role. And the fourth application is so TTL, transistor logic. In this logic also we are going to use 8000 FPGA. What is the advantage of this? This advantage of this one is a high speed. In a high speed controllers we are going to use this 8000 FPGAs.